Hi everyone, today I'm going to be discussing this paper called Instant Neural Graphics Primitives with the Multi-Resolution Hash Encoding by folks at NVIDIA. So in this paper, mainly consists of two parts. On the algorithm side, it proposes multi-resolution hash encoding, which is an efficient, general, and simple input encoding method. On the implementation side, the authors implemented fully fused CUDA kernels for several tasks, which speed up training and inference time quite a bit. So let's begin by understanding the title. The first word of the title is instant, so let's see how instant it is. So in here, the author shows that they can train a nerve within just 6 seconds and get good results. The author also shows that they're able to train a signed distance functions within just 3 seconds and get good results. And here, the author shows that they can do real-time rendering of nerve that's traditionally costly to do because you have to do ray marching for all the pixels at every viewpoint. To show that this is real-time and not recorded, the author has this tool to apply some computational photography techniques here. Like they can apply blurring effects and also changing focus. And these operations are all applied in real time. So now we know how instant it is. We can move on to the next part of the title, which is the neural graphics primitives. So what the authors mean by neural graphics primitives is just an object represented by queries to neural network. This type of network often has the structure of taking in position and output some kind of attribute with extra parameters as input. We'll see some example next. So the most basic example is an image. One way to think about image is that it takes in 2D pixel locations and outputs RGB color. You can use a neural network in place of an actual image with the same input-output for sure. It's not that interesting if it's just a regular image, but if we have a gigapixel image, replacing it with a neural network can potentially save space while maintaining the image quality. Another example of neural graphics primitives is signed distance function, where the input is also a location and the output is the distance to the surface. Nerve also follows the same structure where the input includes a position and the extra parameter here is the view direction. The output attributes are RGB color and density related to that position. So now we understand the first part of the title. I'm going to talk about the main algorithm part called multi-resolution hash encoding. But before that, I want to refresh your memories on the importance of input encoding in nerve. So recall that before passing your input 3D coordinates and view directions to the downstream neural network, there's an important step here where you transform the input into some higher dimensional space consisting of sines and cosines of different frequencies. This step is crucial in allowing nerve to learn high frequency details, and the authors calls this encoding scheme frequency encoding. And without it, your reconstruction results probably going to be blurry. But there are some downsides of frequency encoding. Firstly, sines and cosines are not hardware-friendly operations, meaning that compared to operations like matrix multiplication, addition, or looking up values in the lookup table, sines and cosines would take much more cycle count than those hardware-efficient operations. And also, the author noticed that it's not able to reflect sharp details in some cases. For example, here, frequency encoding struggles with sharp details. So here the author tries to learn a signed distance function to reconstruct this, to represent this gear. But then you can see the results for frequency encoding here. It's pretty poor and it's nothing like the original gear. So then the author proposes multi-resolution hash encoding which is simple, general, and only involves hardware-efficient operations. Now I'm going to walk you through the process using 2D images as an example, but it can be applied to 3D as well. So given an input, the first step is to add a grid structure to the image in different levels of resolutions. Here, for simplicity, we only add 2 levels of resolution, the blue grid, which is 2x2, and the red grid, which is 3x3. In actual implementation, the author uses 16 levels of resolutions. And before the next step, I want to bring back your memories on hash tables. Like hash tables is a data structure class that stores keys and values. And the hash function takes as input the key and returns an index that's within the size of the hash table. So then for the second step, for simplicity, let's just take a look at the 2x2 grid, since the operations are the same for all resolutions. So the second step is to only look at the corners of the grid that contains your input and hash it. In this example, the corners of the grid that contains input x is these 4, right? These 4 are the corners of the grid that contains input x. So then their location is 1, 1, 1, 2, 2, 1, and 2, 2. And we'll take a hash function and that takes as input these locations and then return an integer for each index. So like for example here, 1, 1 got hashed into 0, and then 1, 2 got hashed into 4, 2, 1 got hashed into 1, and 2, 2 got hashed into 7. And the next step is to look up corresponding learnable feature vectors from a hash table of size t. So since these integers represent the index to the hash table, we'll look up the learnable features that's stored inside this hash table. And then to get the actual features for your input x, we want to do linear interpolation of the features at the 4 corners. Yeah, and the linear interpolation is done by weighing the features of the 4 corners by the distance to the input position x. So weighing, these by this distance, weighing this by this distance, so on and so forth. And then the final step is to concatenate all the features of input x at different resolutions, and also concatenate the extra parameters here. And finally, we're ready to pass in this vector to the neural network. And so to put it all together, we first apply a grid structure to the input and only look at the grid that contains the input and hash its 4 vertices or 4 corners and look up its corresponding learnable features and linear interpolate them to get the actual features for the input x and concatenate the resulting feature across all different resolutions along with the extra parameter and then pass it to the neural network. So there are a couple points here I'd like to emphasize. Firstly, this encoding scheme is general enough to work for any neural graphics primitives and can potentially be applied to other types of neural networks like transformers. Second, all the operations involved here are hardware friendly, including the hash functions, so every GPU thread can do this. Lastly, table size t is a trade-off between the quality of reconstruction versus the storage. The reason why the table size t is a trade-off between quality and storage is because of collision. So collision means that 2 different keys returns the same index after being processed by a hash function. So like this. These 2 keys got hashed into the same index. So that's a collision. In our case, that means 2 different vertices are assigned to the same bucket in the hash table. And when the resolution is coarse, meaning that the number of grid vertices is much smaller than the size of the hash table, then collision is unlikely to happen. So here in this example we have 9 vertices and the hash table size is 1000, so the collision is unlikely to happen. So when you have around the same number of grid vertices as the size of your hash table, collision would very likely to happen. So in this case we have 400 vertices, but the hash table is just 8, so there'll definitely be a lot of collision. And you can probably see that collision is a bad thing if you don't handle it right. Like in data structure classes, they teach techniques like linear probing or quadratic probing to deal with collisions, but here the author doesn't do anything to resolve collision and argues that it's okay. And the reason for that is because collisions are statistically unlikely to occur at the same vertices for all levels, even if at one resolution 2 vertices collide. The features at other resolution can compensate for that. And since we typically use reconstruction laws to train these tasks, when collision happens, the vertices that are more important to final reconstruction will dominate the gradient average. That being said, the author includes a set of results that shows the effect of hash collision by comparing with another method called Encoding, which is very similar to multi-resolution hash encoding but without the possibility of collision. And you can see that the surface of the SDF reconstructed gear is a bit rough compared to that of Encoding, and the author attributes this artifact to collision. So some implementation details here. The number of levels of different resolution used in actual implementation is 16, and the hash table size T is 2 to the 14 to 2 to the 24 depending on the tasks. And the number of feature dimensions per entry F is 2. And the course's resolution is 16, and finance resolution is 512 to this huge number. So we talked about the algorithm side, and for the implementation, I just want to talk about the speed up by fully fused CUDA kernels. The term fully fused just means that every operation is on GPU and data doesn't leave GPU until final output. So here, the speed up by the fully fused implementation of the small neural network is around 5 to 10 times faster than TensorFlow implementation. And when putting all the operations needed in training and inference on GPU, that will bring around 10 to 100 times speed up. So overall, the fully fused implementation can potentially bring up to 1000 times speed up. Finally, the results. The first result I'm showing here is small neural network configuration chosen by the authors. It's extremely small compared to the vision models we used to. It only consists of 2 layers, and each are 64 neurons. And the reason for that is because the author thinks this is a good balance between the reconstruction quality and the training speed. The next result here shows that the hash table size T is a trade-off between quality and storage size. So as you can see, as the table size increases from 2 to the 12 to 2 to the 22, you get increasingly good reconstruction results. And here the original RGB image is around 470 megabytes. When the table size is 2 to the 22nd, you can see that with just 1/9 of the storage, we can represent the original image in very great detail. Like you can see the hairs here, you can see the skin textures, you can see the lightings are exactly the same as the original image, which is pretty amazing to me. Well, firstly, I'm impressed by the representation ability of the small neural network, and secondly, I'm impressed by the painting itself. Like, how do they paint this in the first place? So I went to look up this painting. It's called Girl with a Pearl Ring, and it's actually a very famous painting. And apparently they use some special techniques here for painting, and you can look it up. So back to the topic of quality versus storage of the hash table size. The size of the hash table also affects training time, because if it cannot fit into the GPU cache, there will be additional data transmission overhead between the CPU and GPU, which is what you see here when the table size is greater than 2 to the 19, and this is the maximum hash table size that can be fit into the cache of a RTX 3090, which is what the authors uses at the time. And the third result here shows that qualitatively it achieves the same PSNR with NERV in just 15 seconds of training, whereas naive implementation of NERV takes hours to train. So to sum up, this paper proposes multi-resolution hash encoding, which is an efficient, simple, hardware-friendly, and task-agnostic input encoding method. On the implementation side, the author implemented fully fused CUDA kernels for the neural network itself and all the training and inference operations, which significantly speeds up the entire process. And that's it. Here are the references. You can look up additional resources from their official website. There are some pretty quick demos and as well as their own presentation. And here's a link to the actual paper. Thank you very much.